Good morning, everyone. Welcome to the online live demo for guided wave screening using Guided Ultrasonics Limited patented WaveMaker G4 Mini. And today we're going to showcase the high temperature inflatable rings and the new and improved high temperature probes. Thank you all for your time today. I hope you will learn a bit more about the GUL technology and how it can help you. My name is Danny Keck, and I'll be your MC today for the session. I'm an independent consultant working with Guided Ultrasonics to help them further establish their presence here in the North and South America by opening their offices here in the Houston area. Today, we also have with us Dr. Brian Pavlikovic, who will be conducting the live demo. And later in the event, we'll hear from Mr. David Bajula from Akron, who's been Akron has been a very good customer of GUL's for many years. I know you're anxious to get into the demo, but I'd like to start with just a bit of about who GUL is and what they do. I'll keep it short, but hopefully informative. Guided Ultrasonics Limited are the world leader in guided wave technology. Pictured here is WaveMaker House, the headquarters in London. In 2019, GUL celebrated their 20th year in business. GUL is a manufacturer, not an inspection provider. And here at WaveMaker House, all the hardware, software, and sensors are designed, developed, and manufactured. Also, all the research and development and improvements are done here at the UK office. GUL also has a very strong academic link with the Imperial College of London, who have the world's leading researchers in guided wave technology. 2018 and 2019, GUL opened two new offices, one in America, in Houston, and the other in Kuala Lumpur, Malaysia. This move was to enable GUL to support their client base locally, which is expanding rapidly. You can see here that they are truly a global company with units in 6 continents. GUL have sold over 5,500 systems in over 50 countries. This slide shows a timeline for the GUL product development and hopefully shows you just how progressive the company GUL is. Certainly, by no means are they an idle company. In 1986, guided wave testing began with a poorly understood signal and the formation of a joint industry project to investigate the signals and determine their values. Within the next few years, as a result of the research, an electronic system called the Dolphin, along with the first solid ring, was produced to assist the research team in further providing the concept of using guided wave testing. In 1998, more and more knowledge was gained, which enabled the WavePro software to be created, and a form of that software is still used today. In 1999, Guided Ultrasonics Limited was formed. Over the next 6 years, GUL had introduced the WaveMaker G3, which still have some working in the field today. During that same time period, the G-Scan equipment for rail inspection, the first subsea ring, and the initial design of Gpim's permanently installed monitoring systems were produced. In 2008, the Gpims was launched, along with in 2010, the high temperature rings, which we're going to see today. 2014 saw the launch of the screening unit, the WaveMaker G4 Mini, and they are continuously creating more rings designed for the customer's requirements. In 2016, the compact rings were introduced to work alongside with the other rings, but with the added benefit of being more portable, lightweight, and easier to use. Our newest member of the family was in 2018. GUL introduced scanning to their portfolio, and the QSR1 was born. GUL continues to develop new and innovative tools based on customer feedback. Look for more to come in the very near future. Industry challenge that we see, according to recent NACE data, corrosion and erosion is a significant portion of the billion-dollar problem that the oil and gas industry face. With assets and plants only getting older, this corrosion problem will only get worse. GUL have a number of solutions to choose from that tackles the challenges of the aging infrastructure. Screening, which we'll learn more about today, is important for an owner-operator to assure the condition of their assets. GUL screening allows for cost-effective, rapid testing of pipelines to confirm fitness for service and identify the areas of concern that require further investigations or repairs, such as minor corrosion, mechanical damage, blistered coating that can lead to further damage, and many others. Identification of areas of minor damage becomes candidates for continuous monitoring. Scanning, which is a quantitative tool originally designed for corrosion under pipe supports or cups, the QSR tool can be used not only for pipe supports inspection, but can quantify areas of internal and external corrosion in pipelines as well. And third solution would be monitoring, when the cost of assessing the pipe is much higher than the cost of inspection. And by performing repeat inspections, you can compare the results and monitor for any change in the condition of the pipe. Monitoring using the Gpim sensors allows for repeated inspections of the exact location and can identify minor changes down to 1% change in the area of concern. This provides valuable information to asset owners about their inhibition programs, as well as allows for prioritization of repairs. So today we're going to be talking about the screening tool, the WaveMaker G4 Mini, and sensor rings, long-range inspection tool to pinpoint areas of corrosion and erosion. Pictured here is a 3-inch hard ring inspecting pipe in road crossings under the insulation, not just the bare pipe that 3-inch ring is mounted to. Cost savings are huge when compared to digging up the road crossing, removing the casing and the insulation, only to find no issues of concern. Screening limited access piping with guided ultrasonics is a very cost-effective way of assuring continued service of pipelines and avoids high cost of close visual inspection. You can see here another setup configuration. We have a laptop loaded with the WavePro software, the WaveMaker instrument, which I believe is one of the original G3s, and a ring on the pipe. In this case, the inspection covers not only the pipe and the casing, but the elevation change in the opposite direction up in here. As we stated, today's demonstration will be done using the G4 Mini shown here in the laptop computer loaded with the trademarked WavePro software. We chose the high temperature inflatable ring for today's demo to showcase the new and improved high temperature sensors. The improvements come from customer feedback, which is extremely beneficial to improving GUL products. In addition, you can see there are a number of other optional rings depending on your specific applications, from extended focus rings, high temperature rings, high definition rings, low profile rings, and even smaller claw type for tubing. Technical specifications for all the GUL products can be obtained from the GUL website or by contacting their sales team. GUL started introducing systems into the United States or into the US and in North and South America in the early 2000s. Here are just a few of the many clients that GUL have in the US and many more around the world. The majority of those systems are still in operation today. However, many have been traded in for newer models as improvements are made. The new Houston office will better serve the Americas by supplying local training, rental equipment, and eventually calibrating and servicing of equipment. The QSR was designed for cups inspection. The initial detection of cups can typically be done by visual inspection. However, the problem most customers are facing is the ability to accurately size the corrosion under those supports. Live lines most times cannot be lifted, and taking lines out of service can be extremely costly. QSR1 provides you with the average and remaining wall thicknesses, which enables sizing of corrosion for accurate fitness for service assessment. Currently, the QSR1 can be used on pipes with diameters of 6-inch to 24-inch and pipe thicknesses of 1/4-inch to 1/2-inch. They are currently working on expanding this range of pipe size and thicknesses. Coating thicknesses of up to 1 millimeter can be tolerated by the QSR. Gpims, or the GUL Permanently Installed Monitoring System. The benefit of this is that the access to test points is only required one time. You only have to dig up one time. You can easily compare the data of each test location, and you have the capability of measuring wall thickness at the sensor location. In these Gpims, there are up to 8 thickness measurements underneath that permanently installed sensor. GUL is planning for more live demos, such as one on the Gpims. We'll certainly be focusing around the installation and repeatability and value added. Keep your eyes out for many of those to come. There's a Gpim system with an optional solar panel for continuous battery charging. Now note that the Gpim system can be wireless via Wi-Fi or 4G, can be wired via LAN, or data can be manually downloaded to a memory stick via USB. In any case, repeated data acquisition are easy and reliable. All the data can be uploaded to the cloud and stored and monitored by others via the GUL Monitoring Studio. Finally, we have special applications products like rail and subsea, where both screening and monitoring devices for subsea applications are available. If you're interested in either of these applications, please contact the sales team at GUL. GUL offers a comprehensive training package where you will learn about theory of guided waves, along with how to set up the rings on a pipe and how to collect and interpret data. With the pandemic, many of us had to make extreme changes. The e-learning from GUL is one of those changes that has become a huge success. While GUL believes that hands-on, face-to-face approach is the best, when certain circumstances prevail, the e-learning approach can make training more economical. E-learning has proven to be very successful, and GUL have been doing it now for almost 12 months and plan to continue that. I hope you've learned a little bit more about guided ultrasonics. I tried to keep it as short as possible. We're going to go on to the demonstration. All of you are muted, and I appreciate that. I'd like to introduce to you Dr. Brian Pavlikovic, and he will be demonstrating live how the WaveMaker G4 Mini can be used in the field. Brian is a director at GUL and was co-founder of the company in 1998. Brian holds a BA, BS, and MS degree in engineering science from Penn State University and a PhD in mechanical engineering from Imperial College London. Brian won a prestigious Marshall Scholarship Award and spent a brief period studying in Lyon, France. His research at Imperial was related to the study and theory of leaky guided waves in NDT. The dispersed software package, which he co-wrote with Professor Lowe, is still sold by the university and was an outcome of his research. Brian has authored a number of patents related to guided wave testing theory and equipment, and is a level 3 in guided wave testing. He is involved with all aspects of the products and services within the company, with specific responsibilities that include software, electronics, and product development, and he supervises a PhD student at Imperial College. Again, can I ask that you all mute your mics so that we don't get any interference and feedback? We will answer all questions at the end of the demonstration. If you want to ask questions, please raise your hand in the chat section. If you can, just type your question in the chat section and we'll come to them at the end. So with now, I'll turn that over to Brian. Brian?
Hi, thank you, Danny. Welcome to all our participants. I hope that everyone can hear me well. We're going to start by showing you the core of the equipment that we're actually going to be using today in order to go and show this demo. So over here we have the WaveMaker G4 Mini, and it's going to be used with a laptop to go and analyze the data running the WavePro software that Danny talked about. And we're going to be using the high temperature inflatable ring here. And then we also have some other options on rings. So Danny briefly went and covered them, so I'll just go and get them out of the way. So this is the compact, which we can go and show you later. It's nice and light and compact compared to the actual high temperature ring, but it doesn't do high temperature. So we want to go and show some difference. The high temperature was originally done probably about a decade ago when there was a sulfidation corrosion problem in California, and we really needed to inspect these pipes quickly. And we were able to go and adapt our existing stuff, go and increase the temperature, and go and get stuff to people so they could go and solve this application problem. And we were able to do that pretty quickly. And then now over the years, as sort of part of our continual improvement, we've gone and tweaked this and made it a little bit better and dealt with issues that people have gone and had. So I just wanted to go and show you, for example, what some of those did. So the way we tend to go and set up our system is you have the wiring and the ring, which is diameter specific and goes and hides everything away. And that allows it to identify to the electronics. And then we have the transducer modules, which can then go move from one diameter ring to the next diameter ring. So you can go and do inspection. So these have been recently improved. In the past, it was relatively fiddly and you occasionally lose pieces. It was difficult to go and move. So we now have a new quick latch system that allows you to just go and click them in real quickly. We've also gone and now made them changed the way that we adjust them. In the past, they used to take a while, so we're now just trying to make it more useful and easier for the inspector. The reason why we want to go and make these adjustable ones are that we can go and basically adapt it for the application area you want to have. So in general, when you have a large pipe, we want to go and use a wider spacing. Everything sort of scales in our world. And when you're testing a smaller pipe, we're going to go and use a smaller spacing. But also the spacing somewhat control what their optimum frequency is. And so if we know if we're looking for, let's say, a small little pit inside of a relatively clean pipe, we're going to want to go and get the maximum size reflection back that we want. So in that case, we usually use a tight spacing, which is the highest frequency we can go and optimize for. But on the other hand, if we know the pipe's corroded and it's a fire water line or it's a buried pipe, we don't actually want to do that. We'll see too many echoes. We won't actually get to where the serious bit is when it's just general corrosion, because we'll be swamped by all the actual stuff that's meaningless. So in that case, we tend to go for the wider spacings, which is our lower frequency and allows us to go and actually get farther and give you better results. So right now, we're going to go and set up this high temperature ring. I'm going to go in the tight spacing. So I'm going to adjust this back down because I know that the pipe we're going to be testing is in relatively good condition. So we want to go and be able to try to find smaller defects. The high temperature rings are nominally rated for 660 Fahrenheit or 350 degrees C. You can get a little bit hotter than that if you follow very special procedures and try not to melt anything. But by standard, we go 660. You can also then go and use the HT modules in normal rings, or other EFC rings that we've gone and made for the last 25 years. You don't get the high temperature performance because those rings melt at lower temperatures, but you can still interchange the modules so you can have a mixture and match. And it's something that we try to go and do in GUL, is to try to go and have as much cross compatibility as we can and try to go and support things for a very long time and continue to go and use them and just go and improve them as opposed to changing them. So we have our ring. We're now going to pretend that we're ready to now go on site. And so first we're going to go and do a little preparation work in order to determine what we go and need, the way we would go and do it in real life. So we'll start with a wave maker. Before you go on site, you normally want to go and do a few little checks. We've sort of built these into the instrument so that you can just go and do it before you actually leave while you're packing for store, so you never end up on site with an issue that you don't expect. Typically, cables always are weak link. They're always going to be fragile. We try to make ours as robust as possible. We've had people use them as tow ropes and still survive. However, there's still the areas that break. So for instance, we've gone and built in a very simple test with a built-in diagnostics on the instrument that allows you to just connect the cable back. We can then just go and it recognizes the diagnostics. We can go do a quick test that confirms that the cable's okay, the instrument's okay. You're ready to now go and pack up and go and do work. In order to go and also make sure that you have good quality data the whole way through, we also have an I button reader. So every qualified inspector is usually given one of these, and this can identify themselves straight to the instrument. You can use the instrument without this. You can say, okay, I don't want to go and log who's using it. But by having this, you can then go and get that in report. You automatically have it logged and verified that it was this inspector who did it. And so it just simplifies the QA and allows you to go and simplify your reporting and end up with good quality results. We also tend to have some other QA helpers. So there's a GPS built in, so you're able to go and find out where you are. It also then, of course, helps your reporting when you're doing 50 shots a day. You can go and find out where you are and just plot them. We also have each test has a unique identifier, so it's based on the serial number and the test ID, which always appears on the top. Then that's carried through all the software. It allows you to sort of guarantee quality, guarantee uniqueness, and simplify your reporting. Okay, so we've tested this. We'll assume the other cable's okay because I've tested it before. So we're going to be ready to go on site soon. Your computer's normally always going to have Wave Pro pre-installed. One thing we have gone and done now is made this basically into a massive USB stick. So if you do go and lose your computer because it's raining and the computers are much more sensitive than the rest of the equipment. You can just go and plug this in. There's a little install. You can install your software and you can keep on going. It's part of our philosophy that when you get on site, we want to make sure that you're always able to collect data. You're able to maximize the amount of time that you're up and operating. So I'm now just going to move over to the pipe area and then we'll carry on. Okay, so here's the pipe that we're going to be testing. We're basically screening this to go and see where there's any issues. We can visually see that it's a relatively clean, relatively good pipe. It isn't hot. I know it's a high temperature ring and it's a cold pipe, but it's what we have. With this one, I've done a lot of tests in the past on hot pipes. We know that the actual data is the same. Just this particular pipe can't get hot because we don't have an oven element into it. The main difference is actually, the amount of PPE you have to go and wear and actual access to the pipe. In general, for most of the site work, a lot of the time and actually the cost is actually accessing your location and getting all your equipment there. So one of the advantages of guided waves is that we are sending waves down the pipe that we don't actually have to be right where we want to go and do the inspection. So if there's an access platform nearby, we're normally doing the inspection from there. If there's a road crossing, we're normally testing from outside the road crossing, we're not actually digging it up. Some of the CIUI, we're only removing a small section of pipe. So we're going to be testing this one. Here's our ring. It's relatively simple. It just goes around. And that means we're basically attached onto the ring. Now we can test through most well-adhered thin coatings. By thin coating, I mean 40 thousandths thick, 1 millimeter. It has to be relatively smooth, but other than that, it's fine. We're usually fine with any noise in the pipe, so we can go and do all your testing online. We're almost insensitive to almost all contents. Since we're twisting shear motion, any fluid loading doesn't really go and affect the results. In order to go, and since we are shear loaded, we have to press ourselves onto the pipe. Now the solid rings end up going and using little springs to go and push us onto the pipe. These use pneumatic pressure. We've gone just for a very simple car pump. The main idea is you go down to Walmart when yours breaks. The pumps do tend to break quite often. And you can go and get another one. So we'll pump this up. We're now ready to go. So bring over our instrument. Okay. Now, since the housing itself has all of our wiring and all of our ID, it's nice and relatively quick. You can put the cables in any way you want. You're not going to be likely to go and catch anything as you're putting it across. So we try to go and make that bit at least as simple as possible. I'm going to get my computer. Again, so. Normally use a USB connection. It's just the fastest and easiest for most inspectors. You can actually use an Ethernet LAN connection, but with the amount of configuration it has, it requires an inspector who's pretty au fait with computers. Okay, so should everyone be able to hopefully see my screen now? So we're just going to run the Wave Pro software. You can see that automatically detects the ring. You're going to go and see down here in the status bar, it's going to show that it's connected to an instrument. It goes and shows you the ID of the ring. It's now determined how we've set up the modules, so we can go and see there. It also gives you here in the inspector, especially when they're new, just a quick review of the details of how you go and use that particular sensor. So this is telling us what the orientations are. So later when we can report the orientations, we're reporting them correctly. So I'm going to do, this is a demo test. We normally record where we're doing the test. And then we can just go and press go and get it started. Now we do have various collection settings that you can go and use, which an advanced inspector will go and do. We allow them to go and override that and do some very advanced settings. However, the vast majority of times you just press on the go. It's been set up to cover a whole range of scenarios. In this particular case, you can now see it collecting. In addition to collecting the actual real data, we're collecting some calibration data to make sure that the ring is okay and the electronics is okay. We're also collecting calibration data that allows us to see what the amplitude of the signal is. The little green lines that you're seeing on my screen are showing the balance between the different segments. This basically is to use to account for the fact that the paint won't be the same all the way around the pipe. Because in a real life, real site, you will get that variation. And we need to compensate for that if we want to maximize our signal to noise. So we have a lot of routines to go and do it. Normally the collections are pretty quick. However, at the time, most people will go and spend this time to go and do some little notes. They'll go and figure out where the obvious features are on their pipe. You can also do things like take a picture. So we can add a picture of our pipe and its location. And that will now go and be entered into our report later. So that when we're doing a whole lot of inspections, we're able to go and tie this up and give you better reports. And so the client is happier. Okay, if we now go and look actually at the result. We can go and see along the x-axis, we have the distance away from the test position. And we go test both in the positive direction and in the negative direction. So we're both doing them both at the same time. There's a section here at the beginning, which is marked in green. That's an area around where the ring is that we don't actually go and see. We can't go and see right underneath the ring. Then there's a gray area where we can go and see stuff, but it's a little bit distorted and it's not always as accurate as we want. And then outside of that, we're going our full quoted accuracy. Okay. I happen to know, because we can go and see the end of the pipe there, that this is the end of a pipe. So I'm marking that as a flange, which is what it's meant to symbolize. I happen to know that one's also a flange. Stuff we can visually go and see. Now we have a series of DAC curves, which then go and allow us to know for a given reflection, and that's what the y-axis is how big of a reflection we're going and getting from a given location. It gives us an idea of how strong that is. Now, typically you can go and just go and assume a given feature like a weld and how big of a reflection that's going to be, and you can go and fit it to that. And that's certainly possible, but we also then have a way that's been engaged here, which is absolute calibration, where it goes and looks at various reverberations in order to go and determine actually the amplitude of the reflection. So we're not actually now using any assumptions in order to go and determine how big that reflection is. Now on a pipe that's above ground that you're able to go and see, it doesn't make that big of a difference because you're able to go and do some follow-up. But when it's buried or you can't go and access it, having that actual real value is quite useful. When we go and look at the y-axis, the plot that we're going and looking at, we end up with, we show two general graphs. There's a black and a red. Now, normally when black is just on its own, it's a reflection from something that's symmetric. Whenever there's black and red together, that's indicative of something that's localized in the circumferential area. And so that's normally a defect. We don't normally look at it in this raw format. We usually use what we call the unrolled display. And this basically looks at where those reflections are coming from, as if you were to cut the pipe down the top. and unroll it. So both the top and the bottom of this upper plot are the 12 o'clock top position, and so the middle is the 6th position. So in this particular case, we can see some very characteristic, once you're used to interpreting these things, reflections. So these two ones that are straight all the way across, very clean reflections, those are welds. So I'm going to go and mark those as welds. Okay, and mark another weld here. Okay, because we're basically trying to go and build up this little schematic that's showing up above the plot, because that's going to be the basis of our reporting and our analysis. It's then going to go and be communicated to the end client. Now we look at this big echo here, and we can see that the red is a very large proportion of the black. It's clear that's, for us, is a very typical defect. So I'm going to mark it as a defect. Okay. So now we can see, in a few minutes, we've gone and scanned, 30 foot of pipe, and able to go and mark that up. Okay. We then also have some advanced stuff that we teach our advanced people, is to go and be able to change the frequency, for instance, which allows you to then go and see other little details and to see how the stuff behaves, so that we can go and check our classifications to go and see if they're more accurate or not. We can also then look at more, we can increase the amount of the resolution we want to go and look at to go and see if we can see some more defects when we go and look even smaller and smaller. Okay. Now, especially here, if I go and look at the unrolled plot, you can see there's a little blip there, and it's a much smaller blip than the other one, but it's still something we want to go and investigate. So I'm going to go and just mark that one temporarily as an unknown. Okay. Because it's something we want to go and we're definitely getting a blip. Okay. And if we tweak the displays, we can usually go and make things appear more clean or less clean. And this is part of the stuff that happens with the training. There's a whole comprehensive training scheme that we'll go and talk about later. Okay. Part of the training scheme, in order to go and really develop people's confidence and actually to go and create good reports, because it's all about getting good reports at the end. We really encourage people to go and follow up their inspection as quickly as possible and try to go and use some of the other techniques that they probably know in addition to guided waves to go and further define what exactly is at that particular point. So let's go and have a quick look at that. I think we have another camera that should allow us to go and see that. And if I can just, on my screen, we're able to, for instance, just go and measure and say, okay, from that second weld, we go back, we can go back 4 foot 1 inches, and we can go and see something. And then that little blip that we saw before is forward 3 foot 4 inches. Okay. So is this camera live? Yeah. Okay. So here we have our weld. Nice, typical standard.
Patricia, we've lost his audio.
Using basically an electrode and salt water. And we got it deeper and deeper and deeper. So this is its final depth, which is quite large. But you can sort of see that we can see semi-realistic defects. And if we go this side and we go and measure that same distance away, that we went and said there was a, was it 3 foot? Yeah, or 3 foot 4 inches. You can go and see there's just a small drilled hole. And we're able to go and pick that up. That's approximately a 1% defect. Okay. So now that we've sort of done our analysis of our data, we'll now try to go and confirm this visually to go and see what's happening. We might want to go and add some extra pictures to our report, for instance. So let me go and take another picture. if my cable's long enough. It's not. We can go and have those saved later for the report. We're now also going to go into our reporting tab on our software. We can say the severe one. We can say visually confirmed large section of corrosion. And for instance, on that small unknown one, we can now change that. It's not unknown, but it's a small defect. We'll just call it one minor. But again, and we also then, on reporting, you can give it, for instance, a overall classification. So we can go and search later all your results, which ones had major issues, which ones only had minor issues. We can go and say what confidence we have on those results. We actually have high confidence in these results because we've been able to go and verify that and used our other techniques. We can go and then tweak our reporting so it looks nice and pretty. And now we're ready. We can go and create a report for our end client. So on this, the easy ones to go and create is just to create a PDF of it. So in this particular case, you just click on a button, you get a PDF. Similarly, if you want to go slightly more sophisticated, you can now export this to Excel. And this then allows you to go and manipulate it into your own systems and put it into your own reports. We also have a summary section that goes and shows you all the files that you've recently dealt with and collected. You can mark a set, or you can pre-select from a given set of days, print all those reports together as one PDF in order to go create end of report days. You can then go and compare, you can overlay your different results, you can combine results together. We have a lot of reporting tools that allow you to help stuff. You can also then go and take your result and you can upload it to the GUL trunk. So this goes into the cloud storage that allows you, anyone who's been now authorized and has a login for that that's authorized for your instrument to go and back download the data. Also, if you need to go and get some review from GUL and some clarification, you're able to go and do that because the auditors can go and look at the data from there. So we have that full trackability and that ability to go and get support. Which then also makes it remind me, in sort of conclusion, the inspector is a very important part of this entire procedure. It's not quite that you're just following a very simple procedure and saying, okay, boom, here, this little area, I've done this procedure and I've measured this thickness. But you are requiring the inspector to take this information that you're getting from the guided wave, which is getting 100% of the volume. It's getting very long lengths of pipe. You're showing lots and lots of information that they now need to then go and interpret somehow. They need to determine which ones are coming from vents in a pipe, which ones are coming from entrances, which ones are coming from this, and marking all of that up. They need to know a little bit what corrosion mechanism they're looking for in order to initially go and configure the system. The quality of the inspector can go and affect the end quality of the result. And so for that reason, we have an extensive training program that's both e-learning, course room-based, and then on-site data review and on-site data help, and then also post-data review. So with that, we hope when you combine that with a good inspector, with the equipment, every time you can go and get nice, good, reliable results. We can minimize our false calls. We can make it robust so that you're operating as much time as possible. And we can also try to have the tools that make the inspector as efficient as possible so they can really add value to the reports as opposed to spending their time. I would like to thank you now for watching and listening and paying attention, and I'll look forward to your questions later.
Thank you, Brian. Very informative, and I hope all of those that are on the call today have learned something about the technology and how easy it is to set up the entire system and collect data. I'd like to move now to the next agenda item, which is kind of a face-to-face one-on-one with one of our users. Today, we're joined by Mr. Dave Bajula, based here in Houston. David is employed by Akron Inspection in the USA and has been for the last 22 years. Dave serves as the general manager for Advanced NDT Services and one of their in-house subject matter experts on non-destructive testing. Dave is an independent subject matter expert in the legal community and is when called upon, and there is no conflict of interest, obviously. Over the past 40 years, David has acquired a broad-based experience in all aspects of NDT and he has achieved AS&T Level 3 in 10 methods. He's a current CWI and has several API credentials and is a GUL Level 2 and has been an active user since 2004. Dave is past president of AS&T, on numerous committees in AS&T, currently the vice chairman of the Certification Management Council and the chair of the ISO TAG Committee. Akron has been an extremely good client of GUL's for many years. Dave's going to share with us today some experiences in working with the guided ultrasonic limited equipment and using the equipment in the field. Dave, thanks for joining us today. I'd like to start with, so I see Akron's been using GUL equipment since 2004. Can you tell me how is it that Akron came to choose the GUL equipment?
Yeah, absolutely. First, I want to say I'm a longtime listener, lifetime fan. So thanks for the opportunity to spend some time with you today. So I had kind of a unique perspective. I joined Longview in 1999, and in about 2002 time frame, we started, like most people, Guided Wave started to become popular. So I've been fortunate enough to be a user of all three of the systems out there, the main systems anyway, the magneto-restrictive type systems, even the early teletest system, and then of course the GUL system, the G3, as you pointed out. In about 2005 or 6, I can't remember exactly when, we perform what we call a PSO in our company. We do a pretty rigorous evaluation of technology, and we do a process sign-off. Includes almost a pseudo Six Sigma gauge R&R study, essentially determining the repeatability and reliability of the equipment, the processes, the procedure, and even the personnel element as well if you need to. And when we did that evaluation process on all three of those, well, two of the systems anyway at the time, the GUL system, won out almost 2 to 1. So we settled on the GUL system in all of its glory at the time, and have been quite pleased ever since, all these years.
Thank you for sharing that. Now, David, give us an idea of some unique situations where you've actually used the guided ultrasonics equipment.
So, like Danny, you're an expert in NDT. It's about the tools you have in the toolbox, right? So
exactly.
It's always nice to have all these tools. About the only one I don't think we have in our company is microwave, but it's fortunate to have all these different tools. And I will give you 2 examples. One specifically was we were doing concrete penetrations for some compressor stations, a midstream company that had some real issues with corrosion problems at the concrete penetrations through the buildings and through these compressor stations. And we're big users of EMAT as well. We were having some problems with our forward EMAT to be able to get good signals with these concrete penetrations, and we ended up settling on using our GUL equipment for that. Short range, high frequency, combined with low frequency, some pseudo things that we did to do interpretation, and we proved to the client we were successful in evaluating these concrete penetrations. So that was a big plus. The second one was just, I got to share is well, there's actually 3, but another one was a client actually
There's probably many, but go ahead.
There is, yeah. Screening of bad pipe is always an issue, right? This particular client had a tank area and a dike area. They had some torrential rains and the dike area didn't drain and flooded with water for about 2 weeks. So this insulated piping, and I'm talking hundreds or thousands of feet of insulated piping, was submerged in water for 2 weeks. And when they the water finally drained, the operations didn't think enough to maybe take the insulation off or check it. So about 6 years later, they started having leaks. Not 6 years later, 6 months later, started having leaks. So we went in and they said, we know we have bad pipe. We get it. But we need to find the worst pipe in the bad pipe. And that is that is a big challenge. It is a huge challenge. So it takes a lot of detailed analysis to screen out all the noise you're getting from the general corrosion, not to mention the distances that you get hampered with, or the less distance you get traveled because of the corrosion. So that was a big challenge. We were successful in doing guided wave to the point where they understood that they needed to remove all of their insulation and replace mostly all their pipe. The last one was at a plant that had we're doing insulation pipe. It was not in pipe rack. It was in a tank farm, and it was a high pressure line. And on a whim, they wanted to do some inspection on this line, and we started doing guided wave inspection. And I kid you not, it was heavier wall pipe, which is a bit of a challenge, as you know, for certainly guided wave EMAT techniques. But to make a long story short, after several GUL shots, we found some pretty good signals and pretty good indications of severe damage. When we did follow-up inspection, came back around and did some C-scan and follow-up on it, we were able to find a 98% through wall that did not leak yet, that saved the plant from having an emergency shutdown. So it was a really good application for our guided wave technology as a screening tool in finding severe corrosion, followed up by the quantitative measurements that we're able to get. And the remaining wall on this 3/4 inch or 875 wall pipe was 26 thousandths, 29 thousandths. I mean, you could have put a hammer up there and just basically started the leak. So the plant was so excited, they documented that formally within their Technic group as a near miss. How NDT finally, solved the problem.
Finally solved it. Yeah, we solve those problems every day. We just don't get the recognition that we need. I think you'll agree with me. So I want to. I'm cognizant of time, and we do have some questions, but I wanted to ask one more thing. So we talked a lot about training and experience and what have you. And the other day you and I were talking, and you brought up the I button, and I wanted you to just share with everybody on the call today what that I button has done exactly.
The I button.
Yeah.
The I button. Yeah, it's the gatekeeper, in my opinion. I use that term quite often in our industry, the gatekeeper. It basically, GUL has done a fantastic job, just not in their training and credentialing of qualified and competent technicians, but the continual aspect where you have to prove yourself and be recertified. This thing does wonders. It tracks everything that you do. It gives you the keys to start the engine, so to speak. And, unless you're just totally bypass this and unethical reasons, I mean, this is the way that they have managed and controlled competency and quality in the guided wave inspection get done. So I really commend them on the I button.
As do I. So thank you, David, for spending some time with us. We could talk forever, but I want to go on because there are some questions in the chat room, and I'm sure everyone's been interested to hear what we've had to say, and because I know I was, and appreciate your time today, son.
You're welcome. You're welcome.
So now I'll go to, I see some questions in the question box. So one was from our friend Abdul Nasser. The question was, has there been any development on guided wave for heat exchanger tubes? And I'll throw that over to Brian.
It has not been a focus in the last couple of years. We do we regularly do a lot of the boiler tube stuff. So actually, the claw here, for example, is set up for a boiler tube, and so you can go and get access to it. We can make these anywhere from 3/4 inch up to 3-inch tube in this format. Above 3-inch, we tend to go more for the solid rings, and you can normally still go and get those in, and we can get other ways of getting the stuff in. And that testing has been extensive. We originally did a T-scan one, which went in from the end. We actually found there wasn't much, so therefore it's sort of been frozen the way that it was about 10 years ago.
Thank you. So there's another question on guided wave and phased array, and how can that help? And I'm not so sure I understand the question, but
I might be able to make a guess on what he's meaning there. I mean,
okay.
the way we actually use our internally, how we actually go and work is almost identical to phased array. That's the way we focus. That's the way we do the unrolled pipe scan. That's the unrolled pipe, then it looks like a C-scan. We're actually using the exact same algorithms that you use in a full matrix capture phased array system. It just happens we're working in a different frequency range, and our thing is circular, so it tends to go and loop back around on itself. But the actual math is the same. We actually are sort of a phased array system.
Abdul Nasser, hopefully that's answered your question. If there are no other questions, obviously, if there are and we don't answer them today, then you can always send the sales team or info@guidedwave.com and go ahead, Brian.
It looks like Patricia just said, it looks like there's another question that just came in. Was it? Yeah, so we have there was a GUL, what is that? GUL monitoring. Is it just wall thickness below the sensor? It can detect corrosion between two sensors. Our GUL monitoring ones are basically dual capability. So we're measuring the wall thickness exactly directly underneath the sensor. We're doing that over that entire band. So it's not just a few little areas, but in that entire band, we're getting a good numerical value. From there, going outwards, it's more in our long range classification as opposed to an exact number. However, when you are in a monitoring situation and the sensor is nice and stable, and especially if you can have the electronics stay there, then you're able to go and look at all the repeats and see how it goes and evolves over time and track it. And that allows your classification to be much more accurate as we go and watch it evolve in time. So we are able to give you a lot more information far down, and then we're able to give you a very distinct quantitative number actually at the process, actually at where the sensor location is.
Brian, there is one more question here. It says, is there an advantage between the GUL system and the electromagnetic system? They say they've used the MSS system or EMATS and found that the reflections from the dirt, rocks, and water on the OD of the underground pipe were challenging to discriminate from actual defects.
Yeah, they definitely would be. Well, at least the system that I'm aware of, they may have changed it. It was basically you're only looking at what we have in ours as the black trace. Just everything is going to merge together, and there's no balance. And any reflection from anything comes back and looks the same. That's the reason why we've made the equipment a lot more complicated to actually have this entire array of transducers. With that array of transducers, we're able to focus, and we're then able to distinguish between something that is just a contact and something that's in a localized contact. We're also then able to go and determine the difference between, by changing the frequency, because we're able to dynamically change the frequency, we know that those contacts behave a lot differently. So we're able to go and, as part of the advanced analysis, people go and look in at how those change. We're able to get much better discrimination than you are if you're able to just put a single band around and just go and pulse it blindly. So it's definitely worth going and trying ours. I think you won't find it to be nearly as big of an issue.
Next question I have here is Gpim's monitoring. Does this monitoring just detect wall thickness below the sensors, or can it detect corrosion?
Okay.
see.
I think I went, yeah, I think I might have just done that one, but yeah.
Oh, okay.
Okay. I'm sorry. So the next one, what we got? What's the difference between EFC and compact rings? So an EFC ring is essentially the same as the high temperature ring, except it's made out of materials that operate at lower temperatures. So it's basically you have the modules, the two transducer modules which go in and out. They can either be our standard modules or the high temperature modules can go in those. The compact rings, you end up with three transducers in a module, but the transducers don't actually move. And then we end up with different connectors to go and choose which transducer rows you want to go and use and or optimize the system. So the way that you optimize it changes a bit. And the compact is a bit lighter, but
what is the range of thickness for the QSR system? I can answer that. It's a 1/4 inch and a 1/2 inch, yeah.
mm-hmm.
And is there plans for increasing the range of thickness? I think they're working on that as we speak. So
Exactly, yeah. It's their sensors for thicker pipe are currently in test.
and I think somebody wants a repeat on the temperature ranges for the high temperature rings.
We're 660 F, 350 centigrade is their nominal operating.
And
Danny,
down to about -40. But in the really cold pipes, you end up you
Danny,
have to be careful. It doesn't ice up on you.
I've used it up to 750F, and I've actually had the QSR one quite successfully at 0.625 wall.
oh, there you go. Thanks, Dave. What's the difference between the HD rings and all of the rest? What's the high definition do for me?
So the high definition is basically higher. They're the higher frequency ones generally. So when the higher frequency really goes and helps you is if you're looking in short distances. So like, I don't know, let's say you're on an offshore platform where you have all these really short lengths. You're not really interested in going 20 meters. You want to go and see in a little 2-meter section. So you're trying to reduce that near field and reduce that dead zone. It's also good at looking actually at interfaces because the higher frequency isn't affected by the interface as much. So you can do a low frequency test and the high frequency HD test. Also the HD is better at finding really small little pits, but it's of course then worse at seeing big patches of corrosion. It will sometimes be a little bit oversensitive if you have patches of corrosion. So it somewhat depends on your application, what's going to be the best, but it's our more sensitive one as opposed to the general purpose.
So the question, and we're getting quite a lot of questions on the QSR, and we're going to be actually doing a live demo on the QSR, and we'll answer all of those questions soon. But and one more here, it says, how does the signal from the QSR react to welded supports? And I think I can answer that. We don't use those currently on welded supports. Is that correct?
We do not have the procedure to go and do it. It is technically possible to do it, but the analysis is extremely difficult, and it's not
Right.
automated, and it's not taught. So it's certainly not anything that we would publicly say that we could go and do and get people to go and do, although it is technically capable of doing it.
So there are some folks asking for a download on the QSR. You can currently, I can't upload those today into this session, but you can go on Guided Ultrasonic Limited's webpage and get all the brochures for all of their systems. So there any other questions? What is the largest diameter we can inspect using screening?
We can go to quite large diameters. I think the largest individual ring we've made is for 60-inch pipe. You can join
That's
rings
correct.
together. And so I think people have done, 72-inch pipes have been inspected. It's, yeah, we don't particularly have a limit. Similarly, we can go and handle quite thin and quite thick pipe. We don't generally have the limits that come up with some of the other systems just because of the way that we go and inspect it.
Probably got time for one more question if anybody's got it. So there's really, the second part of that question is how do you inspect large diameter pipes, and it's really no different than the small diameter, you know? Yeah.
Yeah, exactly. The principle is exactly the same. I mean,
Right.
again, as we showed, the modules are adjustable. Normally, you'd end up using a wider spacing just to go and get scanned and make it more stable, make it easier to go and put on, and also then makes the interpretation very similar to using medium-sized pipes. But the actual the process is almost identical. So
And
it's a mechanical thing. They do get heavier, and
oh, oh
you
yeah.
know exactly. So that's that's the main issue you go and have is the physical stuff. But the actual
So
application is the same.
any other questions from the audience? I don't see any. Maybe Patricia, can you see any more?
No,
Getting a no from her too.
I got a no from her also. Yeah.
Okay, so look, with that, I'd like to say thanks everyone for attending and making this live demo a success. Hopefully, it's been very informative for you. Look forward to having you on the next few that we do. I know there's some more planned, one on the QSR, one on the GPIMs, and probably more to come, especially the new release in the next couple months. So with that, I will say have a safe day and stay well. Thanks, everyone.
Thank you all.
Take care.